Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Author Series. And I am delighted to have Aylin García Soto with us today. Hello, Aylin.
Hello, Frank. Nice to be meet with you today.
Well, it's so nice that you'll be talking about your very awesome article, which we'll get to here very shortly on this May 12th of 2025 as we record this. And speaking of that date, Aylin, what's your geolocation and is summer happening yet?
Well, it's New England, so there's always an asterisk to the summer. For instance, it was almost there was a flood warning on the weekend, and right now it's sunny. So,
Okay.
yeah,
Okay. Um,
I'm in Hanover, New Hampshire. Yeah.
cool. I'm sort of in the opposite. I'm out here in Phoenix. We are in the desert, and we are definitely rolling into our summer months. So we're hitting the triple digits already. So
Wow.
really interesting. Very cool. And Eileen, what do you like to do for research?
I like Endorfs, honestly, and I also like anything that has variability, which is very broad.
Yes.
But it explains my transition from doing black holes and X-ray in undergrad to
Yeah,
dwarf stuff now.
very cool.
Everything's related to H alpha and variability and time and yeah.
Very cool. Very cool. Very nice. And that is going to bring us to this very awesome APJ article. It is open access. It's the open access era, people. You can go grab a copy for free. Go get one. Short term, Balmer line, emission variability in M dwarfs. And Eileen, take us away.
Yeah, for starters, I want to acknowledge my co-authors because I handpicked them.
Ah,
So usually we have the advisor as the second one,
uh-huh.
but this was a collaboration with someone I went to undergrad with.
Nice.
And so my second co-author is actually it's actually a postdoc at Nashville.
Nice.
Sorry, at Vanderbilt. His name is Garish. And he helped me a lot with motivation and writing this paper, especially since he's looking at flares a lot. And I his recent work in fumes is also really related to this.
Ah,
The
okay.
third one is my advisor.
Heard of it.
Um, she's actually the one who moved Garish first, which was impressive for an
Okay.
advisor.
Yeah.
She's great, and she does a lot of MDorf work, and so she's well known in that sphere.
Very cool.
Um, my fourth, well, the third co-author is Ward Howard. He also does a lot of with UV and flares, and he did the modeling part of this paper.
Ah, okay.
Yes. And then the next two is Alejandro Nunez and
Mhm.
Stephanie Douglas,
Yep.
both of which bring in they do clusters and they do like a high young open clusters, and they do a lot of work with luminosity and finding that in relation to activity. So like activity versus rotation, but also a component in luminosity. And they care a lot about binaries sometimes.
I bet they
And
do.
yeah,
Especially in an open cluster.
yes, exactly. And so they're well versed in the luminosity part of this. And
Hmm.
there's this term called chi factor, and
Uh-huh.
um they're experts in that. And
Sure.
so I used all of my co-authors, and they were very helpful, and I'm very grateful to have them on my paper.
What a great shout out. Lovely shout out.
Thank you.
Okay, let's go. Endorphs.
Yeah, so M-dwarfs are the most abundant stars in the galaxy, and that sounds very redundant, but they make up a lot of the stars. They're also very targeted, maybe more in the past now, since I've learned that people are going to the easier side of stars, which is K-dwarfs.
Okay.
But as of now, M-dwarfs are very important because they have all stars are thought to have planets, but M-dwarfs are smaller, and so their planets would be closer in. And so with the new kinds of methods of finding exoplanets, you can get transit method and radial velocities very easily for M-dwarf systems. However, because they are so close in and they're also very magnetically active,
Mm.
it would not be the same as thinking what Earth looks like as the sun when the sun was younger. They're actually much more active than a younger sun.
Hmm.
And so it's really important to learn about the activity on these things if we really want to talk about the atmosphere on the planets.
Okay.
Um, because they can destroy the atmospheres, but also,
I'll go right off.
yeah, it can tell us what if they have one or not and stuff like that.
That's true. Okay.
But also the composition. Yeah.
Which I like.
Yes. Um, and so one of the most emergent fields is transmission spectra on exoplanets,
Mhm.
and they're very, very heavily dependent on the star's light and also surface features on the star. They make a huge difference and they can mask signals. And so a lot of these papers really try to nail down what that surface looks like, but we don't really know that much about what it looks like since there's only a few M-dwarfs that have
Yeah.
direct imaging. And so other ways we
Mm.
can do, and we also don't really have the bestest models in comparison to stellar models. Solar models are really good, but M-dwarf models are complicated because of the magnetic dynamo.
Yep.
It's not the same for all M-dwarfs. Well, that's the current theory. The current theory is that the solar model transferred to partially convective early M-dwarfs,
Okay.
whereas later fully convective M-dwarfs don't have the same layers internally. And
Yep.
so it might be a different model.
Okay.
However, the issue is that if you compare both types of M-dwarfs, they're similar.
Okay. Interesting.
Except for maybe like evolution, but they're similar in the sense that if you compare their activity versus their rotation, there's not a clear indicator. It's like, oh yeah, right here, this is partial and this is
That one.
fully.
That one. Right.
Yeah, they're pretty similar in that sense.
Hmm.
Um, yeah, so it's a complicated star, and that's why I say that
Lovely.
the I'm not saying that the models are bad. I'm just saying
Let's not say that.
I'm not saying that. That's not what I'm saying. What I'm saying is that it is complicated.
Fair enough.
That's what
Absolutely.
I'm saying.
I absolutely agree with that one.
Yes. Please don't blackball me in the field. I'm not saying that. I'm saying that they're complicated.
Never. You're here.
Um, yes. And so yeah, so part of the inspiration of this was to learn more about these M-dwarfs magnetic fields because again, they're very active, but we don't really sure about their dynamos. And I'm not a theorist, and so one way that I try to approach this issue is by using observational stuff.
Perfect.
And basically, uh, this paper and my previous paper are actually connected in the sense that they're following up on my advisor's paper in 2017. So in all 2017. Um, in that paper, she looked at amplitude. So if you stare at a star for long enough, you can get the brightness over time and you can see modulation in it.
Yes.
And long enough, you can get a rotation period. And so she found amplitudes of those modulations and she compared it to rotation.
Cool.
And also to H alpha, which is a very it's an indicator of magnetic fields on stars.
Hmm. Okay.
And when she made the comparison, she noticed that there is a relationship, but it was very scattered. And this relationship has also been seen in other type of stars. So like Natsu et al. 2015
Okay.
and Yamashita 2022, they looked at calcium H and K
Yep.
and compared that to the amplitude. And they actually found that when you have increasing amplitude, you have increasing strength in calcium H and K. And that's sort of what was seen
Okay.
in Newton et al. 2017, but
Hmm.
the H alpha is much more scattered. And we'll get to that later, a little bit later when we create that relationship.
Okay.
But something that is also seen in M-dwarfs and H alpha and other Balmer lines is that there's short-term variability.
Yes.
And by short term, I mean 15 to 60 minutes.
Okay.
And this we're seeing in a handful of other papers, which I have listed, but the one that I really reference a lot in this paper is Medina 2022
Okay.
and Garisha's paper, Dururi 2023. And
Mm-hmm.
so I heavily focus on those two because some of them, some of my objects overlap, but also Garish is on my co-authors,
Yes,
and
it
he did
is.
a lot of stuff that I implement in this paper.
Okay.
And then I also cite myself a lot, which,
Awesome.
yeah.
Well, at least it's just G23, right? I mean,
Yeah, it's not like, well, it's because a lot of this, I did a lot of the
yeah,
similar
yeah, I
setup
know.
and
It's a
stuff.
it's a
Yeah,
it's a buildup. Yeah, yeah.
yeah,
All good. It's all good.
yeah. And so in this paper, you will see basically um, re-exploring the relationship between amplitude and H alpha luminosity, but also for H beta, H gamma, and H delta.
Okay.
And we'll also see information of short-term variability for those lines. And that's sort of what creates the structure of this paper.
Thank you.
But also information about flares, because that is one of the leading theories on as to what is causing the variability in the short-term scale.
Okay.
Yeah, so my sample um, is section two. Um, my sample is a combination of targets from Fouquet et al., Caselli, and Rayners. 20, all of them are 2018. And they did a large study of finding V cyanide measurements. So these are rotation information
Mhm.
for M dwarfs.
Okay.
And all of these targets are less than 13 days
Nice.
because of one of the instruments we use. It has a observation period of 27 days, and to get a period you need at least two humps so
Yes.
you can
Make
like
sure it repeats.
hold it exactly, make sure they repeat. Actually, technically it's supposed to, it's been proven that you only need 1.5, but we did two, so it's 13 days. Yeah, and so in our sample originally, in my previous paper, we discarded stars that have this term called Rui, which is from Gaia. And for uh bigger stars, there is a much more conservative 1.2. But for M dwarfs, because they're so variable, sometimes Rui is not the best indicator, and so we increase it to 1.6.
Okay.
And what Rui means is that it's a sorry. It talks about it's sort of like a way you fit for individual stars to see if this is an individual star versus a multiple.
Ah, okay.
And so this is saying basically anything that has this Gaia value greater than 1.6 is thought to be a binary.
Right. Okay. Gotcha.
Yeah.
So it's a
Whereas anything
binary
below
cut. Okay.
is likely a single, although sometimes there are binaries that are below that value. And then the next component that I also discarded for that other paper, was a test contamination ratio of 0.2.
Okay.
And that one was calculated in a paper by Rampali. I'm forgetting the year, but in my other paper, I do reference the
Mhm.
specific paper. And so in that paper, there was information given to
Okay.
calculate this number. And so that the general idea is um, what is the contribution from a neighboring star? So how do you know that the variability is from this star, not the other star? And that's sort of that metric.
Fair enough. Okay.
So we pick anything that's less than 0.2 because anything above has a larger percentage that is contaminating.
Elimination. Yeah.
Yeah.
Okay.
And so those were the original criteria of discarding. But in this paper, we actually don't discard those. We just call those binaries, likely binaries, candidate binary.
Mm-hmm.
And furthermore, there's a full table of 93 targets listed in
Cool.
table one. And
Cool.
we're only using 77 of those because 77 of are M dwarfs. The rest of the 93 are Titari stars, and so we don't actually know if their final form is an M dwarf.
Right.
But we included it because we took data on it, so why not?
Okay.
Um, yeah, and for this observation, we actually use data from Yeah, sorry. We also, again, we limited the period based on
Okay. We'll
13 days
check it.
because it's half. Yes.
Yeah.
Um,
Okay.
yeah, so for this project, we used two different spectrographs. We used the Ohio State Multi-Object Spectrograph, or OSMOS,
Osmos.
and we also used the mod spec, which is another telescope on a different observatory. It's the same observatory, it's a different telescope though. So
Right.
one's a 2.4 and that one's 1.3. And Dartmouth has time on this. And these are both considered low resolution. And so I don't have the fancy looking shapes for H alpha and beta that you see in other papers. These are just Gaussian looking things.
Fine.
Yeah. And we honed on really for ModSpec, we honed in on H alpha. So there doesn't have much, most of that data doesn't have the other Balmer lines, which we went up to H delta.
Okay.
Um, some might have H beta, but they're mostly honed in on H alpha.
Okay.
Yeah, and so now that we have our data set, we found spectral parameter, the stellar parameters, because these are actually very important to our follow-up observations. So section 3, um, we we got the parallax from Gaia DR3.
Yes.
Some of them don't have DR3. They have DR2, and then others don't have even DR2. They have like there's this paper from Dittman et al. That has parallax.
Okay.
Because they don't have DR3 is an assumption that they were not resolvable. And
Yeah.
so because of that, we also consider them candidate binaries. Yes. And for the other component we needed was absolute K magnitude. And so for that, we used
Yes.
Gaia's parallax to get distance.
Okay.
And from the two mass all sky catalog, we got K magnitudes, and then so we got absolute K magnitudes.
Cool.
Yes.
Very cool.
Um,
Okay.
so in the next paragraph, I talk about how it's the same page, sorry.
Sorry.
Yeah. It's the last part of this page. For the stellar masses, we actually used a relation from Mann et al. 2019,
Okay.
and it was for M dwarfs that are 0.75 to 0.7, and so that's within our range. We actually cut it shorter at 0.5, but that's within our range. And they have a package on GitHub that you can use. And essentially for that, you need the absolute K magnitude, you need parallax and stuff. And once you
Yes.
submit, you put all that in there, it sort of finds the masses. The paper itself uses binaries to learn more about masses, and there's a bunch of relationships in that paper. And so it shows you there's a tight correlation between absolute K magnitude and temperature and like other different types
Okay.
of um, parameters.
Okay.
Um,
I'm with you.
yeah, yeah. And so the next page, we still use Andrew Mann's work. The next page.
Yep. Yep.
Sorry. We still use Andrew Mann's work for stellar radius. Um, there wasn't a uh, package for it, but there is a relationship within that paper.
Yes.
And for that, you will still need parallax and magnitudes. The other parameter that we looked at is effective temperature. And although there is a relation within the Mann papers for this, it depends on metallicity, and we did not have metallicity. So
Yes.
instead, what we did was use that absolute K magnitude,
Okay.
and the Pikal and Mamajek table, the 2022 version,
Mm-hmm.
they have a list of effective temperatures and also a list of absolute magnitudes in
Okay.
K.
Okay.
And from that, we extracted what our temperatures would be.
Mm-hmm.
And yeah, from that, we can also, so from the 93, as I said, we looked at 77 because if we cut by an effective temperature for 100K,
Right.
0.6 solar magnitude, which we actually, the largest one's actually 0.42. I misspoke. But, and we cut by radius as well. Maybe not in this paper. It's interchangeable mass and radius to cut. They give you the same value.
Oh,
We get 77 M dwarfs, and
well,
that's our final
okay. I'm with you.
observation. Yeah, cool. And so the next section, we talk about the light curves themselves. So I mentioned that we used spectra on the ground, but for photometric data, we use tests because
Mhm.
we know when test is observing. And so we can be very uh sneaky. I'm just kidding.
I was
We
gonna say
can be, we
picky,
can
but
be,
okay.
we can be sly, and we say, oh, test is observing at this time. There's observing these lists of targets. We can go to MDM and observe these targets around the same time.
Nice.
And
Good.
so we can get data that matches.
Mm-hmm.
We'll
Mm-hmm.
talk more about that later.
Mm-hmm.
And we look at 2 minutes versus 20 seconds.
Yep.
Um, it honestly becomes 10 minutes later because we've been it. But for now, we use
Yes.
we do 20 seconds and 2 minutes. And then we use this machine learning tool called Stella,
Mm-hmm.
a convolutional neural network. And so it's a flare detection algorithm by Adina Feinstein.
Yes.
And it was trained on 2 minute test data. And the more I use Stella, the more I learn there's more things you can do with it. And so now I have a more updated thing that I'm doing.
Cool.
And it's not in this paper, but I'm starting to understand Stella more and more and more.
Nice.
Yes. And so it has an indicator of non-flare and flare. And what we're doing is that we're saying anything that's above 0.5 of this indicator is a flare.
Okay. Okay.
Yeah. And so we're removing the flares, but only to put them back later. But for now, we're removing the flares.
Fair enough. Yes.
Some of the flares were not found by Stella, maybe because their shape was not defined in the parameters within the model,
Right.
or they were on the edges, mostly because they're on the edges.
Okay.
They don't have a full shape, and so it's missed.
You got yeah.
Yeah. To reduce the effect of that, we bend it to 10 minutes.
Okay.
But then we also do Gaussian processy fitting. And so
Mm-hmm.
we're fitting the trends with two stochastic driven simple harmonic oscillation,
Uh-huh.
which just means that it does a nice uh, fit and modulate, like periodic modulation. And
With you. Mm-hmm.
I'm not going to talk that much about it, but essentially we fit using Gaussian processes this data, and anything that's around 4 times the residuals aren't root mean square is removed. So the
Okay.
outliers are removed based on this fit.
Right. Okay.
Yeah, and that's what I want to say about that. And so if we scroll to the next page,
Uh-huh. Let's see. Equivalent with. We got some kind
yeah.
of. Okay.
So now that we have rotation periods, because we can also get rotation periods once we're fitting
Mm-hmm.
with Gaussian processes. So that's using star spot. We can get amplitudes because now we have no effect in flares, supposedly. There's
Right.
still some that escape, but there's mostly no flares.
Right.
And you can get the amplitude. Instead of using a sinusoidal curve and getting the amplitude that way,
Okay.
what we're doing is using this method called RVAR, which was in Basari and McQuillan for Kepler type observations. And
Mm-hmm.
we're just taking that for test observations as well. And so if you imagine you have a data set of 100
Okay.
100 fluxes, you
Okay.
get the 5 highest flux and then the lowest 5, and then you subtract it. And then we're dividing it by 2, so it's technically semi-amplitude, but I am using
Right.
semi-amplitude and amplitude interchangeably.
Okay.
And
Fine.
so that's just another way of getting RVAR. And it's a better fit than sinusoidal curves because some targets don't have a
All right.
sine-like
Yeah, exactly.
repeating
Too
pattern.
much variation
And
up
it changes,
time.
right? It changes over time. And
Mm-hmm.
so that's
Mm-hmm.
how we're getting our amplitudes.
Okay.
And so the next section, we're going to talk about subsection. We're going to talk about how we're getting luminosities. And that's where Alejandro and Stephanie really come in
Cool.
because they did this work a lot in their beehive cluster papers.
Yes.
Um, Before that, so we for H alpha in and other Balmer lines, the method of getting what the strength of the line is different from calcium H and K. There's this thing called S index. So if people use calcium H and K, they'll know about it, but we use equivalent widths.
Okay.
And that's basically thinking of like if you have the area under the curve, you find a region that has an equivalent width, and that's what that is.
Okay.
So essentially we find what the equivalent width of H alpha is, but then we also have regions for the continuum, which is very close to H alpha,
Right.
but it's like supposed to represent the continuum around H alpha. And we also have something called equivalent width basal,
Yes.
or quiescent is another word you can use. Because these targets are very active in their short periods, they're always in emission. So technically we don't have the equivalent
Width
at the yeah, exactly. We don't have it at the quiescence level or the basal level.
Right.
And so there's this function in Newton et al. 2017 where the group noticed that there is a mass dependence on maximum absorption. So H alpha is always in absorption in most stars, but it needs to be heated up to become emission.
Yes.
In that process, there's a maximum absorption that it reaches before it turns to emission.
Yes, I'm with you.
Yes. And so that maximum is dependent on mass. And so from that equation in that paper, you can use the mass that we just found, and we can find what that would be for these stars.
Cool.
And subtract that from our measured equivalent widths. Yeah. And that's what we're calling equivalent width relative.
Relative EW. Okay.
Yes. Okay. So that's an important note. If we're comparing this paper to other papers, they might have not done that part.
Oh, right.
And so
very different
yeah, exactly. Yeah. It doesn't change it that much, but there is some change. Yeah, and so from equivalent widths, because it is dependent on equivalent width doesn't tell you about the luminosity of that line. There's also a lot of dependencies in there where it is in the spectra is important. And so instead of equivalent width, we really want to use luminosity. And so the next section is we're finding luminosity for these Balmer lines. Yeah.
Okay.
Oh, another note about equivalent relative, it's only for H alpha because the beta, gamma, delta, and they don't go through that process. They're just emission lines.
Yes.
Okay. Yeah. Or they're non-existent. Sorry, they don't go through that process.
Too.
Yeah. Yeah, so we want luminosity instead of equivalent widths. And so what we do is that we're using this method from Walkowicz.
That's good enough for me.
Lucian Walkowicz. Sorry, I'm very bad at pronunciation.
Sorry about that.
That's okay. It's on me. I should have practiced. But yeah, so there's this method of using this factor called chi. Instead of like doing a true flux calibrated spectra where you have the true flux on the y-axis, and then you can just get the area on the curve. Instead of doing that, we just find a factor chi where it's F0 over bolometric luminosity. So the luminosity of the entire star. And F0 is basically dependent on your line. So that's where the regions of the continuum near the emission line comes in. And also, it has to do with, if you scroll a little bit up for the next section, basically you're using Phoenix stellar models. So these are M-Dwarf templates. And you're calculating F0 from that.
Okay, gotcha.
Yeah.
I'm with you.
Yeah. And then there's a section where I compare archive values with like several papers that have used this method. So like Nunez et al. 2024, Douglas et al. 2014, and then like the original papers that used chi. For the most part, I think there's agreement. It is very dependent on regions, but also how you found the bolometric luminosity. And I think that's where the discrepancies come from. But for now, we're consistent with Nunez et al. 2024. That's where we're using the same code. Our regions are slightly different. Yeah. So
Okay.
if we
Mhm.
continue,
I'm with
yes.
you. I'm with you. Okay.
Yeah. So that's the setup for finding amplitude and luminosity for each of the Balmer lines. So in
Cool.
the next page, I believe we're going into the results.
Cool.
Yes.
Okay. Balmer decrement.
Oh, sorry, there's one more, and then we're going to the
There's
results.
Balmer decrements. Yep.
Yes, it's an important
Mhm.
prior to know. Essentially, Balmer decrement is a way to describe variations in chromospheric activity. So you're instead of directly comparing H alpha to H beta, H gamma, delta, and all the other ones,
Uh-huh.
you want to normalize it by the same thing. So any discrepancy is highlighted better because you're dividing by the same thing.
Yes.
And in the in papers, they usually use H beta or H gamma, but because most of our stars have H beta and not all of them have gamma or delta, we're using H beta.
Yes.
Um, and
Okay.
so
Uh-huh.
this part essentially
Uh-huh.
what's highlighted is that it's talking about there is a notable
Right.
Balmer decrement. So if you have a flare, you'll see your decrement decrease rather than increase.
Yes.
So flat could be like five, a number of five. Let's say
Okay.
your decrement is five. And if you have a flare, you'll see it decrease.
3.
Yeah, three or something like that. And it
The border.
tends to follow your equivalent width but reversed, or your luminosities but reversed.
Reversed. Yes.
Yeah. Again, it's you can't directly compare them, but it's there is a baseline that needs to be removed.
Mm-hmm. Mm-hmm.
Otherwise, you're like probably there's noise involved. So you might not be exactly comparing them.
Right.
And so even though we did all of this, it does tend to match a little bit with the equivalent widths, but reversed because it's decreasing.
Yes.
Yes.
Cool.
Yeah, so the results. If we scroll up, I'm just gonna do this by figures, figure
Sure.
two.
Figure 2. Let's go to figure
Yeah,
2. Figure 2. And I was right there. Here we go. Figure 2. Bang.
yeah. So in
Article.
figure two, what I did is I plotted four plots where you have R-var versus the luminosities.
Okay.
And do note that it's not actually luminosity, it's luminosity over bolometric luminosity,
Yes. Fraction. Mm-hmm.
but I call it luminosities.
It's okay.
So
Mm-hmm.
it's more of me using that interchangeably rather than it being the same thing.
I'm with
Yeah, so from you have H alpha top left, and then it goes
you.
down bluer wavelengths. So
Beta.
bottom
Yeah.
right is delta.
Huh.
And there's also less stars as you go. Some stars actually either didn't have H gamma or H delta
Right.
because it was noisy at the end, or because they just didn't have them.
Okay.
So that's an important note to have, and that probably has to do with the strength of the heating in the chromosphere. These are all chromospheric lines. And so you can kind of see that they're all scattered. They're generally increasing with increasing amplitude, the luminosities, but they're
Yeah.
scattered.
Yeah. Yeah.
Something that may make this seem like a horrible plot is those error bars, but they're
I
not
don't
error
think it's so
bars.
terrible. I don't think it's so
They're
horrible.
not error bars, though.
What are they?
The error bars are much smaller. These are range in luminosities.
Yeah, from the variability. Uh-huh.
Yeah.
Yes.
So each star has,
Uh-huh.
well, some of them, not all of them, have multiple spectra. So some of them we just sat at the telescope. I did some research, listened to some music, and I just let it go
Yeah.
for a couple of hours.
Let it rip.
I think up to 2 hours.
Okay.
And their equivalent widths change within that time. And that's what those regions are. They're
Very
not
cool.
actually error bars.
Very cool.
Yeah. It makes it cooler than it seems. And so if we scroll to the
I think
next,
it gives you a really nice visual sense of what the intrinsic variation of the star is.
yeah, I also think it's important because a lot of studies use a value of H alpha And I think this highlights the point that if your data is not contemporaneous, that might have something that might be a problem, but not necessarily a problem.
Because you may have picked it up in some state that is not
It
representative
does,
of some
yeah.
average, or let's just call it. Right.
Yeah, like the state might not be the same for what you're
Yes.
comparing.
Yes.
Sometimes that matters, sometimes it doesn't. For this, it doesn't matter because initially for the Newton et al. 2017 paper, it wasn't contemporaneous data. This is, and we still get a similar value. So like in this case, it doesn't matter.
Okay.
Um,
Nice
so
figure.
in the next section,
Okay. Snippets.
sorry, can you go up a little bit just to make sure I didn't miss anything? Oh
Absolutely.
yeah, and another thing for those plots is that um these are using that criteria I mentioned in the beginning, and these don't have any candidate binaries in them.
Excellent.
Yes, that was the thing I missed. And then
Okay.
next page, page
Cool.
6,
Mhm.
7, sorry.
It's all good.
Yeah,
Snippets.
snippets. And so for this one, we want to talk a little bit more um, through the text, just
Hmm.
so I don't miss anything.
All good.
So if we scroll a little bit down,
Hmm. We got the Balmers, and then
oh, I guess not that one. Section 5.3, I think.
yeah, here we go.
5.2.
All good.
Section 5.2. Sorry.
Which I think is up a little bit.
It's below. Yeah.
How am I missing this? I'm blowing
Yeah.
it.
No, it's okay. It's okay. It's confusing. Um, so 5.2 is a little bit below. Yeah.
Thank you.
Yeah.
Okay.
Yeah, so I've just mentioned that there's ranges in luminosities for these Balmer lines. And so something that we noticed actually is that variability increases towards higher order Balmer lines.
Mm.
So H alpha is less variable than H delta.
Yes. Okay.
The
Yep.
way I like to explain that is so these stars are always in emission. So think of it as there's an event that causes the chromosphere to heat up more.
Okay.
There's just so much H alpha can go. There's not like there's like a ceiling that it hits,
Yes.
and so it like goes to the higher order Balmer lines, and
Hmm.
so they become more uh they have more strength. But H alpha is like basically stationary.
Right.
Um, it
Cool.
does get a little bit higher. There is some variability, but not as much as you would see from these lines that previously weren't there. Maybe they're there now, stuff like that.
Okay.
Yeah. And so if
Gotcha.
we look at figure 3,
Yeah.
ignoring the flux, because remember, these are not flux calibrated,
Yeah.
but also
Just
these are continuum normalized. And by the continuum, I don't mean the continuum of the entire star, just the region that was
around.
around it. Yeah.
Hmm.
So ignoring the height, if you look at the variability, which we defined as 16th percentile versus 84th percentile. So what we did is that we had these targets
Wow.
list all the equivalent widths. What is the lowest 16th number? What is the highest 84th number?
Hmm.
And basically that's what we're showing. And you see that there is some variability for H alpha, but as you increase to higher orders, there is a much
But
bigger difference.
yeah. Yep.
Yes.
Hmm.
Um,
Hmm.
whereas the black line is the median. And if you do notice, there's error bars on these, and they are pretty big. And so something that might be problematic with this image is that are we accounting for signal to noise and
Right.
error bars? And
Right.
so that's when we come up with equation 2, which
Okay.
is sigma intrinsic right next to it. We wanted to incorporate errors. So we did that with sigma measurements.
Mhm.
And we wanted to incorporate that difference we just saw in figure 3, which is sigma observed. And then we're dividing it by the median measurement. And
Okay.
so that's accounting for the error bars, and that's accounting for error. Sorry, accounting for error bars is accounting for that difference, and it's also dividing it to be normalized,
Right.
to be consistent.
Hmm. Hmm.
And so each star has one value.
Okay. I'm with you.
Yes. For each line, for each Balmer line. So one
Correct.
number for H alpha, one number for H beta, etc.
I'm with you.
And if we go to figure 4,
Okay. Now we're going to take a look at those in figure 4. So let's slide down to figure 4. Here's our variation. Okay.
yes. So we have that value, sigma intrinsic on the y-axis, and then we have Balmer line on the x-axis. You can, it's a little messy, but if you pick one, you can
Good.
see that it increases towards H delta.
Yes.
And this is
Excellent.
incorporating errors and all that stuff I just mentioned.
Cool.
The difference between the two is that the second plot is weird. It's not really following that trend. Um,
Right.
these are all visually inspected, so I couldn't find a reason why they would be wrong. Um, and so
Okay.
like for the circle ones, H alpha starts small, then it increases to H beta, and then it goes down again.
Down again.
I couldn't find a reason why. I visually inspected all of these and I was like, okay, that's what the code is saying.
Well,
Um, yeah, and I mean, one of the theories for me was, is it because it's a binary? But no, the second one also had the first plot of that has binaries as well. So I
yeah.
can't actually explain this.
Okay.
But
Mysteries.
the
I love
general
mysteries.
trend, right, this is why I mentioned the complex of M dwarfs earlier, but the general trend is it increases towards the higher orders. Um,
Generally. Hmm.
yeah. And so that was an interesting study. And then just to wrap up on the variability, if you go down to the histogram,
Sure. Figure
um,
5. Let's sum them up. Okay.
we now have like the density versus the same value intrinsic variability, and how much stars there within each bin.
I'm with you.
And basically you can see it shift towards the right.
Right.
If you look at the bottom x-axis, you can see it shift towards the right.
Mm-hmm.
I would say that H delta is not representative, but
Error, maybe.
it's what we have. But yeah, this was also seen in Durutti et al. 2023.
Yeah. Okay.
Yes, and so he was very valuable in this.
Very.
Um, yeah, so that was it for the intrinsic variability.
Okay.
The other thing we do in this paper is that we look at the light curves and the spectra together. And
Good.
so if we scroll up a little bit to 5.3 this time, I think.
5.3. Let's go up to 5.3, and I did pass that early. Here we go.
Yes.
Uh-oh. Just
So
oh.
yes, there's some differences and they can be explained.
Like that.
Yeah, so this is where I mentioned Medina et al. 2022 because she did a study of H alpha variability short term and she had photometric data to accompany it. And so she found flares in both, but then she also found this target that actually the H alpha rotates with the modulation seen in the light curve. And that was like the only object, and that object was young.
Okay.
And so we'll mention that later. But for the top part, what I was just saying is I was explaining how a flare occurs. Basically, it's a magnetic loop. It I like to explain it in Ghostbuster terms, which is they cross streams and then the top part split up and then
Yes.
the bottom part. Yeah.
Very good. Nice
And
analogy.
that's what a flare is.
Nice analogy. Very
Yeah.
good.
Yeah, so I'd say a little bit more in there, but essentially each flare has a they're not all the same. They have different energies and stuff
Different
like that.
energies,
And
and there'll be some distribution of those energies.
yeah, exactly.
Oh,
And they're also represented differently on light curves versus spectra, and we'll get to that.
true.
Um yeah, so the subsections here we look at different plots. So figure 6 is the first one.
Okay, I'm with you. Figure 6. Let's go down. There's our distributions, and here we go from individuals. Okay,
Yeah, so this one's my favorite, and I'll tell you why in a second.
that's good because I chose it as the poster image.
Awesome. Um, yeah, so this is hard to explain just because there's so much going on, but essentially let's look at the top left.
Okay.
The first subplot is the light curve. So it's flux over time.
Mhm.
And just because barycentric Julian date is very confusing, what I did is time since first observation in the spectra.
Yeah, yeah,
So it
0.
tells you right here that we observed it for like 2 hours,
2
basically.
hours. Yeah.
And so the top part is the light curve of tests,
Okay.
and those blue dots are binned test points.
Okay.
We binned it by the uh exposure, not the exposure time. We binned it by the same difference in the data for spectra. So like if we took an
Oh,
image
because you
every
want
two
to do this
minutes,
comparison one-on-one, right? Yeah, yeah.
yeah, so if we took an image every 2 minutes, then test is every 2 minutes.
Okay.
It wouldn't be that. Actually, it is. It is for this because this is showing the back part is showing 2 seconds, 20 seconds, and the this version is the blue is showing the 2 minutes.
2 minutes, yes. Okay.
Yeah.
Okay.
This is a good show for if you care about flares, maybe look at shorter cadence than longer cadence.
Right.
That has been used as in proposals. But essentially that's what we're doing here. We're making the cadence similar.
Yes.
And so the second subplot is equivalent widths versus time.
Okay. We got stars and circles.
Yes. So the stars are, I believe, H beta, and the circles are H alpha.
Okay.
Yes. And then below we have the Balmer decrement or
Uh-huh.
BD,
Uh-huh.
where we're dividing by H beta. And so you only see H alpha
Mm-hmm. Mm-hmm.
because H beta is basically one.
Mm.
Um,
Mm.
and you can see that it's variable, basically.
Yeah.
Intrinsically, it's variable. The highlighted regions
Yeah, the
in
blue.
blue
Yeah.
are Stella, what Stella considered a flare.
Gotcha.
And so you see three big ones in the
Two,
beginning, and
three,
then
something.
debatable, and then there's like this bump towards the end that you can actually see in tests,
Uh,
around 100 minutes.
yeah. Uh-huh.
You can see that bump also in the Balmer decrement,
Yes, you do. Okay.
reversed, and then you can also see it in the equivalent widths.
Yeah.
That was not a flare.
Yep.
At
Yep.
least that wasn't considered a flare.
Mm-hmm.
Could be. I don't know. But there's situations where you see things match, and that's impressive. But then there's situations where you have the beginning where you don't see anything match. It's just
Yeah.
variable.
Okay.
So that's night one. If we scroll to the right, this is my favorite, night two. Mostly because although the light curve looks kind of boring, no offense, Tess. I worked there. I should be able to say that. I'm just kidding. There's a nothing burger for the light curve on night two.
That's a very
And
technical term there.
mm,
Nothing.
but if you looked at equivalent with, there's a lot
Yeah.
going on.
There's a lot going.
This is actually
Much.
trimmed because it was hard to see. But there's actually more data above the 0.7. And
Yeah.
so but it was like harder to see the more smaller features, so we just chopped it up.
Yeah.
And so what you're seeing here is that you're seeing multiple flare events.
Yes.
So a flare is defined, if you look at H alpha, it's a little bit easier on the eye. But essentially a flare is defined by a short rise and a long decrease.
Mm-hmm.
And that's somewhat what you're seeing. So you see like at least three flares here where
Yeah.
if you look at the
Definitely.
highlighted regions.
Yeah.
The first one's small.
Mm-hmm.
The second one doesn't, in my opinion, does not reach the continuum level.
Okay.
It's flaring again, and then it flares a third time, and that third time has a second bump.
Bang. Yeah.
And so that's considered a complex flare,
Okay.
where it doesn't have the rise and the fall. There's like multiple,
Bang, bang,
it's
bang.
multi-structure. Exactly.
Yeah. Yeah.
And so that third one, which is defined by the third shade region,
Mm-hmm.
is actually what we model later on.
Okay.
And so we're going to jump to
Yeah.
figure 10 later. But this one, you can see that you can't actually see the peak because, again, we trimmed it.
Yes.
But it's peaked where that blue line is, and then you see it decrease. And that the how long it decreases is like 30 minutes, which is a pretty long flare in my
Yeah.
opinion, but I
Right.
don't actually do flares.
Okay.
This was me dabbling in flares,
A lot
but
of it. Yeah.
yeah, I think 30 minutes is long in my
Pretty
opinion.
long for the tail.
Yeah.
Yeah.
Yeah. And so that one's that information is seen but flipped in the Balmer decrements. And so you
Hmm.
see a lot of
Hmm. Structure.
trouts. Yeah.
Yeah.
Um,
Cool.
yeah, so that one's a pretty interesting one. So that's night two.
Okay.
And then night three is the bottom one.
Okay, let's go down there and then we'll zoom out a little bit so we can kind of compare all three at once.
Yeah, so night three is a little bit more on the it's just variable.
Hmm.
We don't really see much of
Bang, bang,
comparison.
bang,
Like there's a flare and test, but you don't really see anything.
bang,
And
bang, bang. Yeah. Nice.
yeah, so that's why there's a
Yeah.
discordance
I
because
see why you like night two better.
sometimes you see something in test, but you don't see it in the spectra. Sometimes you see something in the spectra very, very clearly, and then you don't see it in tests.
Yeah.
And so if we again look at night two's third flare, the one that has multiple peaks and lasts 30 minutes, so
Yes.
the third highlighted region, and we
Uh-huh.
jump to figure 10.
Figure 10. Keep that in mind, folks. Let's go down to figure 10, 8, 9. Keep it in mind. And there we
Just that one, because that one was the most interesting.
go.
This is using a radiative transfer code,
Hmm.
an atmospheric model code called
Good.
Ryden.
Okay.
Yes, it's Kowalski et al. There's several years, so I'm just gonna say Kowalski et al. If you look up Adam
That's good. There's
Kowalski,
more than one instrument paper. Good. Okay.
it's also based on a previous code. All of that is cited in this paper. This was Ward's work, Ward Howard. He's been using Ryden to fit spectral flares. He does a lot of work with multi-wavelength data,
Uh-huh.
and basically what you're seeing in this first plot is that there's a lot of models. Those are indicated by the taglines.
Uh-huh.
Each model has a specific format. I'm not going to go through all of it, but the F11, F12, F13,
Yes.
that's just the 10 to the negative, not the negative, 10 to the 11, 10 to the 13, 10 to the,
Uh-huh.
yeah, those
Okay.
are like the energy fluxes of the
Okay.
flares.
Okay.
And so they're just showing you all the flares, all the models that in this case has, and they're showing you what flare area coverage fraction it would be. So like if
Mm.
you had a flare called the one in the red, the
Yep.
fraction would be like 0.17 or something.
Okay.
Um, so that's the like the area of where that flare originated.
Yeah, right about there. Yeah.
Yeah. And if you scroll down, the reason why that one's in red is that there was MCMC ran through all of these models to fit that night two. So night two only has H alpha and H beta. Unfortunately, although that exciting, it didn't have delta and gamma. But
Well,
alas, it was fitting basically those models. And if you look at the y-axis, it gives you all of the units I failed to mention. But essentially the best fit model is wait, I was right. It is 10 to okay, I was confused. Sorry.
it's the red one.
Um it's sorry, if you read the caption, it gives
Mhm.
you all of the units that I failed to mention. So this is a 10 to 11 ergs per second
Yes.
centimeter squared.
Okay. It's a flux.
Um basically like a 17 to 37 killer electrovolts.
Yep.
And so this is like the best fit model using this write-in code that we can get for that night too.
Fair enough.
And it's basically the only one we got some semblance of what the flare strength is. Um,
Cool.
yeah, so that was pretty interesting. So if we scroll back up and look at the other targets, those will fly by much faster because
Well, it's all good.
there's less information.
Let's see. So we did, here we go. Figure 7. This is another.
Yes. So this is another one. This is actually a binary, but it's a wide binary.
Good choice.
Um, wide as in I believe it's wide.
Yeah, you know what I'm gonna
Um,
ask. Like, how many AU is that?
actually, it might not be wide. It might be that the companion is so dim that it doesn't matter. Like it's not
Got it.
contributing. I think that's what it is. Because otherwise I remember the separation. I don't.
Yeah.
So for this, we have the same format where we have light curve equivalent with
Wow.
Balmer decrement.
Okay.
And that first one, that first night has a very beautiful test flare.
Indeed.
But then if you look at the equivalent with, it's not there. Um,
Kind of a mess.
it's very, very messy. Um,
Yeah.
and if you look at well, actually, if you look at the Balmer decrement,
Yeah.
H alpha specifically, you see that there is somewhat a decrease there that can, I mean, it might indicate that there is a flare.
Yeah.
There's also a second little decrease,
Yeah.
and it might correlate with the little bump I see in tests. But again, these are like so tiny that I
Those are,
wouldn't trust them.
yeah.
And so this can be an indicator of there is no flare there's no direct flare in the spectra in this
Okay.
case.
Okay.
Yeah. There could be other things going on in other wavelengths, but for tests, there is no clear correlation here.
I'll come back to that. Okay.
Yeah. And then you kind of see something similar for the next few nights where there is not much going on.
Same,
Um,
kind of the same. Very,
yeah, pretty
very
flat.
flat. Okay.
Yeah.
A little bang, baby bang,
Little two bangs, two baby bangs,
two
and
baby
then
bangs, boom, boom,
pretty
and
flat.
flat.
Yeah.
Yeah. Uh-huh. Okay. I'm with you.
And so now we have an instance where you have a good test flare, a very nice bright test flare, and you don't really see it. Maybe debatable.
Mysteries.
Maybe.
Mysteries.
Maybe you see it in the spectra. And then there's the previous one, which was a very clear
Clear one.
indicator of a flare in the spectra, not in tests.
Yeah.
And so the third object in this series of plots is sequestered in the corner because it wasn't that interesting.
Okay.
So something that is important to note is that when you have a large, if your star is dim,
Bang. Yes.
your your cadence is long. And so
Yes.
for these ground telescopes. And so we're
Yes.
missing a lot of information for this one.
Okay.
And I can't really say much about it, just that it
Bang.
had a longer cadence. Um,
That.
yeah, it's pretty flat.
Uh,
Except for maybe this around after 70 minutes in the second night.
yeah, a little bit.
There's some weirdness
A
there.
little bit there, a little bit there. Yeah. Uh-huh.
Yeah, but it's pretty flat.
Okay. Overall. Mm-hmm.
Overall, pretty flat. And then the fourth of the series is this Amber Medina target. Um, I'm forgetting the non-tick name of it, but it's much shorter. But yeah, this target was observed at Medina et al. 2022. This is the one that I mentioned earlier was a young
Yes.
star that matches H alpha with the rotation modulation in the light curve.
Cool.
We couldn't exactly replicate what the Medina et al. Paper did, likely because we didn't know what phase she used.
Okay.
But we do see that for the
Uh,
top plot, this is the
uh,
recreation. For the top plot, whenever the light is dimming, you see a brightness increase.
yes.
And so this is an indicator that there might be a dark spot rather than a bright spot.
Uh-huh. Uh-huh.
So we don't actually know what the surface of these things look like. We don't know if the contribution to the modulation is a bright spot or like a faculae or a pelage, or if it's
Something.
a
Right.
dark spot like sunspots
Sunspot.
or
Yeah.
star spots. For this one, we think it's a dark component just because it's reversed. So if you
Right.
see dim, you see more.
Yeah.
Yeah. If
Mm-hmm.
it were a bright spot, they'd look exactly the same. Um,
Cool.
yeah, so we observed this again, and unfortunately, we didn't get a full rotation.
Right.
But we did get snippets. We're seeing,
It's consistent.
if you look at the first half of the second plot,
Mm-hmm.
you're seeing the same thing where you have like increase in the light curve, and then you have a decrease. Yeah,
Flux. Yeah.
yeah.
Yep.
I don't know what the second half's doing.
See,
It honestly looks like it's doing the opposite.
not quite as deep as a dip. Up, up. A little bit of scatter there.
But
Scatter.
it's mostly scattered. So
Yeah.
yeah, so that one was interesting. So
Hmm.
it would be no surprise when we try
I'm
to
gonna come
do the
back to those.
same test that Amber Medina did in her paper where she was comparing the the equivalent width versus phase and the light curve using an F test.
Okay.
It just tells you which hypothesis is real. Does it match versus does it not match?
Mm-hmm.
Hers numbers were way stronger. Uh, you can see it visibly, clearly,
Yeah.
but also statistically true. And then we did it for ours, and we don't find
Mm-hmm.
nearly strong enough numbers, but there is some consistency. And
Okay.
so we can still say, yes, it is probably still rotating with the period.
Okay.
Yes. I
Good.
want to tiptoe on that because we
Yeah.
did a p-value test, and p-value around zero point 0.5 and below is what's statistically significant. But we got 0.08.
Okay.
And it's like so close. You're so close. Uh, it's like really close, but it's marginally significant.
Mm-hmm. 91%.
Whereas for Amber Medina, you get 0.002, which is
Really good.
wonderfully significant.
Right.
Um, yeah.
Okay.
Yeah, and so I believe those are, let me just double check.
Yeah. We got.
If we scroll up a little bit,
Uh-huh.
just making sure I hit all of the notes.
Yeah. You're playing the
Um,
orchestra. You're doing really well.
thank you. I play guitar. Uh, yeah, I think we got everything. I didn't really explain right in that much, but if you can see the previous people I mentioned, so it's Carlson and Stein, those are like the origin.
Yeah. Yeah.
But then uh Kowalski did a lot of work. And so this paper is using the most recent write-in version, which is Kowalski 2024. And
Mm-hmm.
then it's using a lot of information from Ward's papers on write-in and flares.
Yes. Very
Um,
cool. Okay.
and that one's in the next page. But yeah, we talked about that one already. We use this to
Generate this.
try to learn something about that second night with the multi-complex flare.
Right. Very
So
cool.
Ward Howard 2023 is that paper he's referencing.
Yes, right here. Here we go. Mm-hmm.
Mhm.
Okay. Yep.
So basically,
Yeah.
the paper amounts to a few things.
Okay.
First thing is amplitude activity plot from Newton et al. 2017.
Yep.
Then the contemporaneous version in Garcia et al. Garcia Soto et al. 2023.
G23. Uh-huh.
Similar numbers. And for this one, this paper, 2024, Garcia et al., still the same numbers. So basically, it's intrinsically scattered, that
Good.
relationship.
Okay.
Not like calcium H and K.
Amazing.
Something I forgot to mention. The reason why I think that makes sense is because calcium H and K, we know how it originates. Any emission from that, we know how it originates. It's
Okay.
collisionally variable, like a collision excitation.
Uh-huh.
But
Cool.
H alpha and H beta and gamma have they have multiple ways of being
Excited.
excited. And
Yep.
so to me it makes sense. It could just mean that we're seeing that it's multiple things happening.
Probably.
But also we don't have calcium H and K. We only reach H delta here. And so we don't actually know what it's calcium doing.
Okay.
But potentially if it were a better fit, it's probably because there's multiple things happening for the Balmer lines
Oh, I bet
than
there.
there is for calcium H and K.
I
And calcium H and K is also a chromospheric line. That's why it's
Yep.
always compared.
Uh-huh.
Um, the other thing is we saw short-term variability, 15 to 60 minutes,
Yep.
and it matches several papers in the past.
Yay.
Specifically Medina et al. And Duruvi et al. And more specific to Duruvi et al., 2023 is that higher order Balmer lines actually vary more
Yes, we saw
the than H alpha.
good examples of that in this paper.
Yeah. There's also discrepancy between flares. There is more in the paper that I didn't go over as to why there might be some discrepancies. For instance, there's a time delay I didn't mention. It seems in the paper that there's a time delay between lower order, so H alpha, H beta, and like
Oh,
higher order H delta and gamma.
yeah,
That
sure.
it seems like it's only a little bit. It's only a little time delay. And that might have to do with like back warming. So heating from top down. And so uh redder lines are higher in the chromosphere, bluer lines are lower, and so like top down.
Mhm.
Um Not by that much, but like
Oh,
top down. That's what I mean by back warming.
okay. Mm-hmm.
Um
Mm.
which is what you highlighted basically. That's the Nooper effect.
Yeah.
Usually used in UV, but we don't have UV either.
I'll come back to
Um Yeah. And so the next thing was we found some indicator that that really young star from Medina et al. Has a dark spot.
that. Okay.
Because once there's dips in the light curve, there's increasing in the spectra.
They went. Different ways.
Yeah. And then the last thing is that we modeled that very complex flare, not very, that complex flare in night two of one of those sources, and we saw that it matches a flux energy of 10 to the 11 ergs per second per centimeter squared.
Yeah, about the tens of
Yeah.
keV. Okay, very cool.
Yeah. And then so from that, I would like to acknowledge a lot of people,
Mm-hmm.
especially these are alphabetical order, so I don't think more than one. In there's it's not by importance, it's by alphabetical order. So
Okay.
some of these people like Adam Kowalski, Medina, uh Zachary Berta Thompson, Sebastian Panetta, not Natsu, Utah Natsu.
Uh-huh.
Um like if you read through the paper, I have cited them, but I also talked to them in person. And
Yay.
at the point where I had no idea where this paper was going, they were very valuable. They send
Cool.
me like, read this, learn this, make sure this is correct. Um,
Nice.
and other people I also thanked. Oh, Kevin Covey has to do with the Phoenix models, and so that's what he's
Yes.
thanked. But then other people that are like at Dartmouth, so like Graham Edward, well, he's now a professor elsewhere. But Burchin, Graham, um, they were very helpful with personal motivation.
There we go. That's
And
always important.
yes, yes. And then the Arcelia and Becky we're also good with motivation, and we met like virtually to be motivated together. And so I
Yay.
thank those people. And then lastly, but not least important, is the people at MDM were very helpful, very nice when I was there, very accommodating whenever things went wrong, which happens sometimes. And then also an observer that's no longer there, but he did a lot of observations for this.
Very
The
nice.
rest was me.
Cool.
But yeah. Yeah. Thank
All
you
right.
for this. This was fun.
Yeah, Eileen, I want to thank you so much for walking us through your very beautiful paper. Very nice.
Thank you.
Yeah. And you kind of hit on it a little bit at a couple of points. And so let me go ahead and push on that a little bit and ask, where do you think we go from here, given the published article? You
Mhm.
mentioned, are there other wavelengths to examine? You
Mhm.
mentioned the possibility of UV. Could we go into the far infrared? Would they might tell us something? There's always more observations to do, so I won't ask that. But but just sort of next steps. Where do you think we go with this over, let's say, the next couple of years?
Yeah, for sure. I think there's two. One is they're both complicated.
Good.
Um, one of them is multi-wavelength.
Yes. Yes.
So Ward Howard was a postdoc for Meredith McGregor. She does a lot of multi-wavelength stuff.
Yep.
And so does he. And so they have papers where they show observational and UV.
Hmm.
Also look forward to Durruti et al. Future paper because he's also looking at multi-wavelength stuff.
There's that.
Um,
Good.
yeah, so it's important to so basically from this paper, all we can get from the flare was this might be the energy. But we couldn't say this is the origin, this is how
Oh,
big the ribbon was. Like there's not that much
could be
information, right?
more
Way more
info.
information. And
Yeah.
so if you use multi-wavelength data, you can get that information. You can say, okay, the origin was it was this big, possibly this big, because again, everything has error bars. And you can say maybe a little bit more about the photochemical stuff that's going on
Okay.
and stuff like that.
Cool.
And so multi-wavelength is very important. Also, there's studies where you know that you might consider something low activity or quiet,
Okay.
but they're not. If you look at the UV, they are not quiet. And
Yeah.
so
Right.
that's a
Exactly.
asterisk. When I said like high activity or like very active, I was talking about H alpha and the
Correct.
Balmer lines.
Correct.
So
Not.
that's something I should mention. Also flares. But like some other stars may look flat always and maybe have H alpha emission, but they're not quiet. They're active in other wavelengths. So that's another reason why it's important to have multiple, preferably contemporaneous. But you
That
can
would be
say something
ideal.
about
That
like
would be ideal.
long term
Yeah.
observations
Yeah.
and that's like the second one, long-term observations.
Okay.
I only stared at these things for 2 hours, and so I couldn't get anything related to rotation modulation.
Okay. So
And
what do you think would be an ideal,
well, the rotate I didn't mention this. I sort of brushed over it, but rotation modulation is related to spots on the surface. So
mhm.
surface homogeneity, heterogeneity.
Yes.
Um, it gives rise to different shapes in your light curve. And so if that shape is repeating, then there's stuff there that is staying there.
Staying there.
If it's changing, it's evolving, right? And so um the evolving part, essentially. Like stare at it for a long enough time. Maybe you're doing tests, spectrum photometry again,
Uh-huh.
but staring at it for a long enough time that
Okay.
you get a rotation period.
Nice. Okay.
So the rotation periods I showed you, they were not 2 hours. They were high, they're bigger than that.
Yes,
And
they
so
were.
like at least a rotation period of observation.
13 comes to mind. Mhm.
Yeah. Um, these were less, but they weren't exactly 2 hours.
Okay.
Um,
Oh, I see. Yeah, it'd be pretty hard to get 13 days worth of observations. You'll
well,
know.
yeah, I mean, there are small telescopes.
Ah,
And
okay.
it also doesn't have to be like you don't have to stare at it all the time
Okay.
because you can't do that because of this, sun
Yeah.
is out.
Understood.
You don't want to destroy your
Understood.
instruments. Um, but there's like ways you can do it. Like maybe if you know the light curve, we were trying to do this, but I didn't stay on it long enough. There was so many targets we were looking at.
It,
Um,
it pops up
different
when it's
parts of the
the minimum,
phase.
when it's going to be in the max. Yeah, yeah.
Exactly, different
Okay.
parts of the
Okay.
phase. We
Okay.
could have done that. So maybe if
Yeah.
like 10 days ago I did the beginning,
Right.
now I did the middle, and then 10 days later I did the end. And so you can get a full phase.
I'm with you. Mhm.
Um, so not staring at it always, but just like enough so you have a complete phase, which is what Amber Medina did.
Nice.
Um, it's easier for the shorter
Yeah.
rotation
Oh,
ones,
sure it
but
is.
yeah. So
Excellent.
those are my two main. This is how it goes forward because the other thing about having long-term observations is that you can see, is this intrinsic variability periodic?
Yeah.
Or is there clear indicators that no, it's probably just like different origins. But we don't know if these are also matching a certain period that's on like star related. So is it a magnetic activity period?
Right. Right.
Because there's more things than just rotation. There's like the
There is
activity
on dwarfs.
cycle and
Uh-huh.
stuff like that.
Uh-huh.
Is
Okay.
it like matching? Is it more uh spot dominated or is it more flare dominated? When the flare dominated is more like crazy and variable and weird, and the spot one's like it's matching the rotation period.
I like them both.
I think it's fun. I think honestly, just stare at it forever and
Very good.
realistically not, but yeah,
Long enough. Cool.
long enough.
It'll be really interesting to see this field develop over the next couple of years. So very
Yeah, for sure. Especially I do want to emphasize this again, but it's very, 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 very important we know what these surfaces look like
yes.
for those atmospheric um like those atmospheric transmission spectra
Yes.
studies. They're trying though. Like I've noticed that um as this field has progressed, we're very entwined. And so more exoplanet people are talking to star people and they're getting
Right.
like better and better at defining these surfaces.
Cool.
And so I'm excited for that as well. Like what do these things look like?
Be very exciting. Very
And
cool.
they're probably different because Mdors don't like
They
us.
are. The whole population of
They're
differences.
so
Very
complicated,
cool. Yeah. Well, it
which is why I like
almost
them.
certainly guarantees variety, right?
Yeah.
Be weird to have something be very complicated and yet march all to the same drummer. So yeah,
Yeah, true.
cool. Eileen, I want to thank you so much for walking us through your very awesome article. Thank you so much.
Thank you for meeting with me and being my hype person.
Oh, you're welcome.
It's very helpful.
And that will do, everyone. And I hope this made your astronomy day, your M Dwarf day, just a little bit better. And we will see you on the next one. Bye bye.